So we've been looking at homonuclear and heteronuclear diatomics and looking at the molecular orbitals and how we would generate the molecular orbitals for those. But what happens when we have more than two atoms? So then we have to turn towards generating what are called symmetry adapted linear combinations of atomic orbitals, or what I'll use for short as SALC, or SALCs, okay? So to show this, how we use this is we're going to start with looking at the compound beryllium dihydride. Okay, and so this is going to be a linear compound. So we can draw the Lewis structure like this. All right. And then from there we need to think about the basis set that we'll be using for the beryllium and the hydrogen. So what we're going to do is we're going to combine, right? We're going to combine atomic orbitals for the ligands, right? And separate that from the atomic orbitals for the metal. And so in this case, or for the center atom, I should say. All right. So we're going to treat these together, these two hydrogens, okay? And so the basis set for each hydrogen will remain the same as we think about, such as dihydrogen, right? We would have our basis set. So first we'll label these HA and HB. Our basis set for the ligands are going to be a 1s orbital from HA and a 1s orbital from HB, all right? So we have two hydrogens involved, all right? There are ligands, all right? And then if we're thinking about the beryllium basis set, right? This beryllium has an electron configuration of 1s2, 2s2, so we would look at the 1s orbital for beryllium, and then also the 2s orbital, okay, within our basis set. Okay, so, and as we'll show, we'll actually expand this, but for now, we can just think of that right now, because what we're going to focus on is how do we treat the two hydrogen atoms when we look at this triatomic species, okay? So in this case, right, if we're looking at the SALCs, we're looking at the SALCs of the two hydrogen atoms, and we're ignoring everything about the beryllium right now. We'll treat that later, okay? So for now, what we want to think about is if we have two 1s orbitals, right? So let's say this is the nucleus of the beryllium, this is the nucleus of hydrogen A and hydrogen B, okay? And so we know what the 1s orbital looks like, okay? And so we can put them, quote unquote, in phase, or having the same phase as each other. And so what we would have is this is the nucleus for the beryllium atom, this is for HA, and this is for HB. And so one way we could draw this is that the two 1s orbitals, so 1s for HA and 1s for HB, have the same phase. And so we could draw one of our, we could draw it in this configuration, or we could draw it where these have opposite phases. Right. So we could draw it like this, okay? And so we can think of this as saying the 1s HA plus 1s HB, okay? Where the signs, right, for the two 1s orbitals for the two hydrogen atoms are the same, they're both positive. Or in this, where they're inverted, right, we would think of the equation describing this as 1s HA minus 1s HB, where the phases are opposite of each other, okay? And so it's important to note here, right, that the hydrogen atoms, right, they're going to interact with the beryllium, not with each other. And so there is no overlap here. These are not considered bonding or anti-bonding orbitals in any way right now. they are not overlapping, they're not interacting either through constructive or destructive interference in any way right now, right? We're just setting up a mathematical function that helps us to collectively describe the SALCs, right, for the ligands, and then afterwards we can then match this to the atomic orbitals of beryllium in a way that allows for constructive and destructive overlap, and that's where we'll actually generate our MOs. But right now we're just treating the 2 hydrogen atoms alone, and we're using a basis set of a 1s orbital for each of them. And so these are the 2 combinations that we mathematically can come up with using a basis set of 1s orbitals. And what we get, again, is we get one where the 2 1s orbitals have the same phase, and then we have a second where the 2 1s orbitals have opposing phase.